Google Cloud Vision is a powerful image analysis tool delivered through an intuitive API. Cloud Vision recognizes and understands a broad set of entities inside of an image. It can read text, human emotions. It even knows that this mango was with high confidence a mango. But at Google, we take moonshots. So we thought, could these APIs do more?
The idea came one day when Miles said to me,
Michelle, does this look too normcore to you?
And I had no idea.
Today, we're sharing the newest feature of the Cloud Vision API, style detection. Now, Vision can tell you not only what clothes you're wearing, but what that might say about you.
Imagine fashion based on data, not feelings. That would be a better dressed world.
We knew we needed experts for this project, so we invited fashion consultants, even elite teenage bloggers to help us figure this out.
Style is intangible, enigmatic even. It's not just about patterns or pleats or when to wear white. Style is an art. It's an instinct. Can it be taught? I don't know.
There's eco chic and boho chic and geek chic.
Fuzzy, goth, hypergoth, those are good.
There's a whole chic list.
Like humans, teaching machines takes time, and the larger the training corpus, the better our predictions will be. We've analyzed millions of images, A-line skirts, fedoras, you name it.
Our mantra here at Google is to launch early and iterate. So that's exactly what we did on this project. We set up a live testing environment in order to analyze an even more diverse set of personal styles. We made adjustments when needed and fine-tuned the algorithm as our training corpus continued to grow.
We discovered that fashion exists not only in the streets, but in the clouds. This is a new beginning in fashion history.
We're excited to bring style detection to the world, because fashion touches all of us.
You only get a few chances to make a first impression. Sign up for the alpha today.
Welcome everybody, and yes, that is a April Fool's joke, and we're not releasing that feature. Sorry. Okay, well, we're going to talk about deep learning and how we're thinking about it at Google, what we're releasing, and in particular, we're going to talk a little bit about TensorFlow. So before I get started, I just wanted to talk a little bit about what is deep learning and applications of that before we jump into TensorFlow itself. How many of you folks have used like a deep learning library like Theano, TensorFlow, etc. before? Okay, just a few. Okay, perfect. So I'm not going to get into too much detail in deep learning. I'm just going to talk at a high level, and for folks who want to jump into more detail, you can find me after the session. We can jump in. So in the end, just to kind of think, deep learning is just another way of applying sort of algorithms on data. It's all about data, and I think one of the things one I will take away from this is the more data you collect, the more clean data that you have, the more labeled data that you have, the better output you're going to have from a machine learning or deep learning perspective. So again, we've used, you can imagine basically machine learning on any kind of data. That's structured data. We do lots of structured data. If you think about what we do from an ads perspective, or how we think of weblog, clickstream behavior, to thinking about unstructured data, how does Google Photos know that to find all the photos of your favorite dog on your favorite beach out of the box? That's the way we do that is through large-scale computer vision models and using deep learning. The other aspect is how do we think about Google Translate? How are we able to basically translate a language from one language to another language, and how do we do that in a powerful manner? And how do we then combine things about both vision models and translate models? And one of the things we recently introduced is when you do Google Translate, you take a photo, it automatically does OCR on that, and then sends it to translate model. All of this in some ways is powered by deep learning models. Here is an interesting scenario. Think about your own use cases. Here is a way we introduced this thing called Project Sunroof. And what it's trying to do in the US is trying to tell you, based on your roof thing, is it a potential candidate for solar panels? right? You can imagine something like this applied to people who are trying to do financial models, and they want to understand based on public domain satellite pictures of shipping ports, and based on economic activity, how is that going to influence financial models? Or if you're a logistics bank things, how do I think about counting the number of crates inside my warehouse? All of that, in some ways, is just large-scale financial deep learning models. Other things you can think about is, more and more, I would say, a couple of years from now, we're going to be using voice as a way to drive how we interact with applications, right? That means how do we understand speech as an interface to your applications? If you can think about it, over 1 billion people use Android today, and almost all of them say, "Okay, Google, play music, open my application." All of that is done by powerful speech-to-text and natural language understanding. And you can imagine this is going to become an interface to most applications down the line. Another simple thing is how do you think about smart reply? I think this is a thing that that's in your, I don't know how many of you guys use Inbox or Gmail. Think about somebody sending an email to you, and there may be some canned responses that you can drive out of the box. Right? This is an example of another case of deep learning and machine learning where we do a simple network, understand the text coming in, says, hey, is there a canned response I can send to this text? And then thinking about how do I then apply, do some natural language understanding to then drive a response to that. If you then translate that to your world, let's say you're doing digital marketing and you want to do campaign management for a thing, so you want to start driving both call center responses, you want to drive campaign management responses, so customer sends you an email to your customer service department, and how do we automate that where you can start sending text back to your customer in an intelligent manner and start scaling what number of customers you can support, right? And the other scenario is, this may be not that relevant for most folks, but you can imagine the models are getting smarter and smarter, where you can imagine sakes where you start training more and more models. A human may say, hey, this is a picture of somebody grilling a thing. And the model understands us based on the fact that it's a grill there, there's a sandwich there, and then applying multiple vision models together to stitch a text together. And of course, models can also start driving new kinds of hard. This is a deep dream machine learning model. It's basically based on images you upload. It starts combining multiple different deep learning models to generate new kinds of hard. And we actually just had an arts exhibition of how machine learning models can generate hard for you. So one of the things, I think a lot of these things has a lot of real-world examples of how you could think about deep learning applying inside your application. Whether it's driving better digital marketing, so you want to do things like sentiment analysis, whether it's adding additional signals to your existing machine learning models. Here's something if you think about is, let's say you're doing price prediction for an apartment, right? Initially, you use things like number of bedrooms, number of bathrooms, square foot of the house. That would be the ways you drive your price prediction. But more and more, people want to understand all the product reviews for that apartment, right? Based on social media, based on product reviews on the site. How do I get signals about that house and feed that as an additional feature into a machine learning model? Then lots of people take pictures of their house. One of the things that people really like about one of the indicators maybe is the house sunny? How are you going to find out if a house is sunny? You have to do some deep learning on the images to see if a house is sunny or not based on the amount of sunlight coming in. That then becomes an additional signal. As you can imagine, more and more, when you think about machine learning, it's not just about doing it on your structured data. It's about how you combining both unstructured, structured, and third-party data sets all together to drive richer models for your customers and for yourself. One of the things that we've seen inside Google is, we've seen a pretty steep uptake on deep learning because we really do believe that this is kind of the next level as people start thinking about machine learning in a serious manner. And really, I think one of the things I hope you take away from this is it's not just machine learning for the sake, but how do you make machine learning part of every user workflow and every user process? Whether it is dealing with invoices coming in from your shipping department so you can do better OCR, whether it's your customer service side, so you're thinking about natural language understanding, so you can do better responses, but how do you automate your entire workflow? One aspect, if you think about machine learning, it's all about data. First, it's all about data. It always starts with data, which is why we're talking at the Big Data Summit. But really, it's not about how smart the algorithms are. The algorithm papers they're all white papers. They're all research papers. They're all been in public domain for 20 years. So it's really not the algorithms that make it that smart. It's really about how do you apply data at scale to get these better data sets, to get these really smart, intelligent models with labeled training data, and how do you have infrastructure to enable that? So that's really one of the key things I think we've learned in Google. That's one of the reasons why we actually open source TensorFlow, which is kind of coming to talk what we want to talk about. So when we think about Google from a machine learning perspective, on the open source side, and I think what I want to focus a lot on is on TensorFlow. That's what we open sourced in November last year. It's already one of the top 5 most popular repositories in GitHub. It's gaining a lot of momentum from a machine learning perspective. And from a cloud platform perspective, we're trying to make it easier for users to enable that, so think of a managed service on TensorFlow. And then for folks who are not ML PhD, deep data scientists, how do we encapsulate all these powerful deep learning models as easy to use APIs? And I'll talk a little bit about that. Okay? So let's talk a little bit about TensorFlow. Before I jump into TensorFlow, questions? I can't see anything, so unless you guys raise your hands, I won't be able to hear it. So when we think about, so this is our open source library for machine intelligence. It's really not just for deep learning, but really it's our open source library for distributed machine learning. And the reason why we call it TensorFlow is tensor is really, we think about it's an n-dimensional array. That's kind of what flows through our system. And flow is the way we enable that is through a data flow graph that drives this process. TensorFlow was announced in November last year, and if you think about it, it's been less than 6 months. It's one of the most popular machine learning libraries on GitHub, so you guys can go look at that. Large number of starts, large number of folks, strong ecosystem. We see more and more people adopting TensorFlow for a wide variety of different activities. And one of the things that we want to do is, one of the lessons learned is Google has been really good about writing a lot of white papers. We wrote white papers for Google File System, for a lot of things that drive some of the big data stuff. With TensorFlow, we wanted to come out to the community and actually share an implementation that the folks can start adopting much faster. So what is it? At its core, what is it? It's a set of C++ libraries that enable large-scale distributed linear algebra matrix multiplication. And then we basically encapsulate that with a set of Python libraries for you to create your own model graphs. So what that allows you to do is give you an easy way for you to write. I'm not a C++ expert, and I do not want to write C++. So from a Python perspective, it's really become the language for data science, allows the data scientists to start creating their own machine learning models, and then you can do prediction on that. And it runs in a variety of different ways. It's open source, so it runs on your own local environment, on your own local cluster. So you can do it runs on both CPUs and GPUs. GPUs really comes into play when you start thinking about large-scale data sets and dense data sets. You're thinking about large-scale image models, large-scale text models, and sparse models. And it's also portable. So you could train a model on your large cluster, on either local or in the cloud. And then you can then take that model and move it to an Android phone. So you can actually do, an example of that is, we actually have some machine learning models on an Android SDK called Mobile Vision, where we can do things like face detection running on your device itself without having to go back to the cloud. Right? So really the power of TensorFlow is it both runs locally, runs in a distributed manner in the cloud, and also portable, so you can actually once your model is trained, move to your device, either it's an iOS or Android device, and start doing predictions at the point of, for almost real-time processing. And I won't go into too much detail, but what I want to talk about is really what we're trying to do in some ways is, if you think about the core of what it is, it's large scale, it's understanding weights and biases, right? In some ways, it's just a curve. You want to understand, I have a bunch of x's that's used to predict the y, and I want to understand the weights for all my x's to determine my y, right? That's really what, in some ways, in a very simplistic manner, what we're trying to do from a machine learning perspective. And the way we would drive that is by passing tensors, so it inputs through the graph. The graph is similar to Spark. It's a DAG that kind of flows, that defines what your model should look like, and you define it up front, and then you then pass this data through. So in the case of something like logistic regression, which is some pretty common classification model, you can imagine some things like where you have a bunch of input, you have a set of parameters, you define your function around how you want what your function to be for your model, and then you try to figure out how do I minimize my loss at basically the lowest point of my loss function that says this is the best set of weights to predict what I want. That makes sense? Again, going back, it says weights of x's to predict the y, and what we're trying to do is just try the little function to define that. And I'll show you some code there. I'm not going to go into too much detail. And then, of course, you can then visualize your graphs, and there's a set of tools that we provide for you out of the box, like called TensorBoard, that tells you to start visualizing your graph, and you can start visualizing how does this overall neural network looks across multiple layers, and you can think about how do I start driving this to gauge something. Majority of folks may not, you can imagine this requires some level of knowledge of deep learning, but really the goal is we want to start enabling this technology to become more and more easy. So that's one of the things from an open source community perspective is where we're working with a lot of folks to say, look, we don't want you to necessarily know 30 lines of Python code to write a simple classifier. How do we make it easier and easier? And there's a lot of open source tools like Scaflow, et cetera, that basically starts layering on top of TensorFlow easier and easier libraries for you to build your own machine learning models. I'm going to skip a couple of things, and let me just show you some code, because this is a Google session, and it just wouldn't be the same if I'm not showing you guys some code. Here is a IPython notebook that we have, and basically what I wanted to show you guys before is, this is what I mean by, so in this case, I'm doing a simple thing of sentiment analysis. I have a bunch of text, movie reviews, and I want to predict if something is good or bad. So you can imagine you would come in, you would define your loss function, you define how you want to optimize it, meaning that in deep learning, it's all about finding the lowest part of the curve, the gradient, where the losses are the minimum. And you'd run it, you train the model, you can start predicting the model right here on the cloud or on your local machine, and you would basically just pass in some data and you can do prediction on that. But the key aspect is now, so this, you can imagine when we talk about TensorFlow, that tells you how you can do it locally. And then now, if you start thinking about larger and more complex models, you then need more than one machine. It's coming back. So if you can imagine, like now you want to start parallelizing your data set. This is really where we talk about distributed training. So this is where you can imagine if somebody wants to do large-scale training across large amounts of data. TensorFlow supports this starting in February. In the open source community, we just open sourced that. So this allows you to do large-scale distributed learning across really large data sets. And why does it matter? So here is a simple ImageNet model that we trained. If you do it on a single GPU, it takes roughly around 3 to 4 days. But if you do it on 50 GPUs in parallel, it's in a couple of hours, right? Time is money. And data parallelism makes it really easy for you to do this at scale and drive smaller training periods. For example, if your data scientist if in your organization, the data scientist is comfortable running a model once a week and figuring out and say, okay, I'll run it on Monday. I have nothing else to do because my model is training. That may not be that big a deal. But in this case, you really want to start parallelizing a lot of the stuff so you can get results back within a couple of hours and start understanding whether your models are actually of the highest quality. And that's really where we start thinking about moving from open source to the cloud, is where we're thinking about this thing. Is one of the things that we've done a lot of time in Google is we have been in the open source ecosystem for a while. We wrote a lot of Google white papers over the years, from Google File System to MapReduce to Bigtable to Dremel. All of this was white papers that we wrote in Google. We wrote some research white papers. Then the open source ecosystem took that and ran with it and built SDKs out of that. And one of the things that we've started doing recently in the cloud platform, we started making products out of that. And that's really where, if you think about BigQuery, it was a Dremel white paper that came out in the second half of the last decade. BigQuery is a product that we shipped. We shipped Bigtable recently. Again, that was basically coming off the Bigtable white paper with an edge-based interface. And TensorFlow is another example where we wrote the white paper, we shipped in this case, we actually shipped the SDK, and we're also shipping a cloud service that goes with that for you to give you a managed service to train at scale. And let me talk about why that would matter. So if you think about machine learning is all about taking data, right, from your data sources. In this case, it's coming from a cloud storage or from your local file system or from your structured data, doing pre-processing on that. For the way to make the machine learning model work is you need to convert that data set, whether it's raw text, whether it's raw images, whether it's raw numbers, into a format that the model understands, right? In this case, we do the pre-processing for you. We give you some help around things like images or text out of the box. We train the model as a managed service, and then we, of course, start evaluating the model for you, understand how well the model is doing. And then the other part is once the model is trained, you then want to do prediction on that, and then we give you as a managed service to run your prediction. So since I'm going to shamelessly troll you guys and show you an image classification model. And because the model's goal is, can I hug this? So I'm going to show you an image, and I'm going to ask the machine learning model to say, do you want to hug this picture, or you don't want to hug this picture? Imagine for you to do something like that, you would have to build this large, complex, multi-layered image. So this is our ImageNet model that we open sourced earlier this year. So this is a multi-layer, I think, of an ImageNet model across many layers, across over thousands and thousands of images to understand a broad set of labels. That's great, but all of us don't have millions of labeled images that you can use today. And in this case, and for example, and this model doesn't have a concept of hug and no hug. So what do we do? So one of the things that we can do in deep learning, which is really why deep learning is powerful, is you can take this open source model, which is used to train thousands of labels, and just basically cut off this last classification layer and say, now I want to add additional training data to understand my two specific labels. Does it make sense? So I have a model that understands the concepts and objects of animals, wine, objects. It understands all what each group of pixels mean across thousands of objects, right? We already have this trained. This model is ready to go. And it's open source. Now what I want to do is I want to come and add two specific labels, hug or no hug. That's it. And so basically, so if I look at what the model will look like is, in this case, so it's basically similar to what we just showed earlier. I would create a simple hidden layer. I'm just going to create a couple of hidden layers. I'm going to create my loss function, and I'm just going to do the exact same thing which I just did earlier when I did image classification. And so and again, I don't have to train it on thousands and thousands and thousands of images. I'm going to train on maybe hundreds of images to show what's a huggable image and what's a non-huggable image. Fair? So let's actually show it. I'm going to show the prediction and not so much the training. So here is an example of, can I hug that? So let's actually run this through. So in this case, I'm going to so here is an image of a Google data center, and let's see what the model comes back in. And hopefully, this is what happens when I try to run. Let's give it a second, and hopefully it comes back from it says not so huggable. This is kind of sad because I love data centers and it looks really cool to me, but according to the model, it's not huggable. So let's do another case where I actually, this is where I shamelessly troll you guys, and I show a picture of a panda. And in this case, hopefully it comes back as huggable. So here's the exact way of, let's give it a second. It's running, and it's running, and it's running. Huggable. Again, so that's an example where, as a machine learning scientist, this is a nice, simple example of huggable and non-huggable, but let's take a real-world scenario. Let's take the case that you guys are a retailer, and you're shipping boxes out of your warehouse. Wouldn't it be nice that since you already have cameras all over the place, you take a camera of every shipment that goes out of your door, and you can find out of the box whether the box is damaged or not, right? You just take a bunch of photos of a non-damaged box and a bunch of photos of a damaged box, and you can use machine learning to start detecting these things out of the box. Let's take another case where you want to do image classification, where you guys are driving things for parts provisioning, supply chain, right? People take photographs of all their supply bins, and you can understand if a box you create another image model of and in this case, the label is part A, part B, part C, part D. And you take photos of all your supply bins in your warehouse, and you can tell immediately if the bin is full or not, right? Most warehouses already have cameras in there. You can start imagining scenarios where you start automating these pieces out of the box, rather than someone having to manually start counting whether I need to fill a certain bin or not. Another example is you guys can start driving, you can start thinking about scenarios from image classification for things like around better, more intelligent ad placement, right? You can start figuring out things like whether something is adult content or not. Some of these can be automated as models out of the box, and some of these may be things you want to build. These are cases for images, but you can imagine this also applies to non-image scenarios when you start thinking about textual data. And the sentiment analysis I didn't walk through that's an example where you can start thinking about where you can do your own image sentiment analysis, right? You drive image data through and you drive sentiment analysis and say, is this a popular product review or not? All of this requires some level of machine learning. So what I want to do is kind of start talking about is this clearly applies as if you have a larger data scientist, you can drive that. So how does this work? How did my classifier works? In this case, I basically had a bunch of images. So I went and grabbed a bunch of images of hugs and non-hugs. So within the concept of hugs, I put things like animals. I put things like flowers and teddy bears. And I labeled them as huggable. And under non-hug, I just put random things from 9-inch nail cover, add album covers to things like data centers and those scenarios and make it non-huggable. And those were just 2 labels. And then I ran it through my classifier. I built a model, and I predicted off that. That make sense? And you can just imagine these things can be applied for whether it's images, whether it's text data, whether it's numbers data. It's the same concept. What I want to transition to is, that's not the Eye of Sauron for the Lord of the Rings fans. It's actually one of the products that we're releasing. So if you can imagine, we just talked about machine learning where you build your own models. But what if you don't want to build your own models but want to leverage pre-existing models? So what we've done in Google is we actually shipped a set of APIs that encapsulate some of our deep learning models. Let me show an example of that. So here is a scenario where we went and basically pulled roughly around 100,000 images from Wikipedia, and we started running them against our Vision API. And we always have to start with cats because you can never have enough cat photos. So we just send this image against our Vision API. When you run it against the Vision API, what we'll tell you is, it's a cat, it's a mammal, I had no idea. There's actually a cat breed called British Semi-Long-Hair. It actually tells you up to that level. And then you can also imagine scenarios where, let's take something that's actually a little bit more relevant for you guys. Let's say I want to do OCR on this image. So let's say I case an image for transportation. There's a street sign. We automatically will come and you can do OCR for out of the box. And you basically will tell you trees, kangaroos. It does automatic language detection. So if you have if you have documents or receipts or invoices in Japanese, in Spanish, in German, or in French, or we support a wide variety of different languages. It automatically does OCR on that, and you can get this text and start driving more intelligent stuff. We have tons of customers who, surprisingly, I never would have thought about it, but one of the most popular use cases for OCR is receipt scanning. If you'd asked me that before I released the product, I would have said no way, but a lot of people really want to start scanning all these receipts and automating that. Another example is logo detection. So, for example, one of the things is you can start imagining things where, let's say you want to start, if you're a digital marketer, people have so far done sentiment analysis on textual data, right? People have been doing sentiment analysis on Twitter feeds, Facebook data, on product reviews. They've been doing that for a while. But if you understand, one of the fastest growing data that's going out in the world today is not text, is not tweets, but actually pictures. If you think about Snapchat, which is one of the fastest growing social media platforms, it's all about images and video. And if you're a digital marketer, you want to understand who's using my product, what are they doing when they're using my product, and are they happy or not happy when they're using my product, right? So for that, you need to understand logos. You need to understand where is my product in this image. 2, you need to understand what are the emotions of the people in that photo, right? Are they happy? Are they sad? And 3 is you want to understand what are the objects that they're doing with the image. Does it make sense? So you can imagine how, if you're a digital marketer, you can start scanning these millions and millions of photos and start understanding how much of these are actually using my product. So in this case, we automatically pull something like, in this case, I'm doing Android logos, but you can imagine your own individual organization and start understanding what are the product logos that you have internally. And then you can then do things like, let me actually show another example. Sorry, you can never have enough cute dog photos and cute cat photos. Let me show an example where you can imagine you do something like face. Let me just pick a file. Sorry, oops. Looks like I lost my face photo, but let me just leave with this thing where I want to do. Sorry, it's what happens when I try to do a real-time video. But you can imagine, so let's extend this demo to see if this guy was actually holding a can of Coke while kayaking. That would be a bad kayaker. But if he was holding a can of Coke while kayaking, we would actually recognize the fact that there is a can of Coke in the picture and the fact that he's kayaking. And we don't see his face that well, but if his face was blown up, we'd actually tell you if the person's smiling or not. But I'm unfortunately not connected to the cloud. And then I'm going to leave you last with my last cat photo of the day. So let me show you a couple. So in this case, let's take the case of faces. Like for example, what we would tell you is we automatically identify all the faces in the image. We'll also tell you if the person is happy, sad, not sad, what's the role, whether they're hangry, whether they're underexposed. You can imagine you can start doing some really intelligent sentiment analysis on the photo based on that. So let me just wrap this up, and I'll come back. And the last one is, so we already shipped a set of APIs. We shipped Vision. We already shipped Translate. So translation is something you guys can use to translate your own things from different languages to English or vice versa. It supports a wide variety of languages from and to. It's in the tens of languages. And we also just shipped Speech API. So if you guys are looking to do speech, so just think of this. You can imagine every day when somebody says, OK, Google, that's actually using powerful deep learning models to do speech recognition. And what we've done is we are using built off TensorFlow. And what we've done is encapsulated as an API, so you can basically do, you have your own speech recognition for your own apps. Well, that's one use case. The other big use case we've seen a lot of people is they want to do transcription. So if you can think, we had a couple of customers who do call center logs, right? So you can start imagining a scenario where your customers are calling in, their calls are recorded, and you can automatically do transcription on that call. And then you want to understand, OK, was that call a positive call for the company or a negative call for the company? And then you want to do sentiment analysis on the call to say, OK, based on the sentiment of the call, should I respond back to the customer or not? Right? So you can start imagining where you start bringing in these powerful deep learning techniques into your workflow. You can imagine some new scenarios that are opening up. So in summary, I think when you start thinking about basically where we think about Google is we're providing both a powerful open source framework called TensorFlow that enables you to build your own models. We're going to make that easier and easier. It's highly popular. We have over, last time I checked, tens and thousands of downloads of TensorFlow today. We're giving you a managed platform to run TensorFlow in the cloud. And then we're also giving you a set of APIs to encapsulate powerful deep learning models as easy-to-use REST APIs for everybody to consume them. That's it. Questions?
Can you say something about TensorFlow in combination with Spark?
Yeah. I think, so the question was TensorFlow and Spark. So right now, if you think about one of the most important aspects of machine learning is definitely around feature processing, right? And you can definitely see use cases of people using one Spark to drive a lot of feature processing and then feeding that into a TensorFlow training process. The other big part is I think there's a white paper that Databricks just released where you could almost run, you could basically pipe out of Spark and run TensorFlow as a separate switches scenario, where you can then use Spark to kind of orchestrate multiple TensorFlow training sessions at once, and then kind of converge back to what I think. And that's a pretty common scenario if you think about machine learning, whereas your first model you create almost 95% of the times is not the model you want. You really want to do almost an hyperparameter tuning where you want to run tens of models in parallel, and that's a good scenario where you could run a single machine scenario of TensorFlow and Spark kind of acting as the orchestration pipeline. So that's something you can do today. So you can basically, it's a white paper that's published, that's out there actually, that shows how to do that. The other part we're also looking at is we are going to be doing distributed training for TensorFlow, and that's another, and I think that's something that is, to me, I think it depends on where the community is going to take it. Right now, I think we already have an implementation that we open source today that's not using Spark Runner, but I think it's using things like Kubernetes to deploy the cluster, etc. Question?
How's the experience with chaotic systems?
Could you repeat that?
Is there any experience with chaotic systems?
Chaotic systems?
Yes.
You mean like time series data sets, or what do you mean, or just bad data?
If I understand it well, the idea is analysis.
Yeah.
And if you have a chaotic system like weather or falling drops or something like that,
Yeah.
does that work?
Yeah. So if you think about it, there's actually this is sorry to be U.S. centric, but there's in U.S. there's a NOAA National Oceanographic kind of they track weather data for the U.S. in the U.S. environment. And you can imagine they've actually really set up machine learning models on how to think about. One of the good things about weather is it actually has lots of really good training data. The key thing for machine learning is training data, training data, training data. The more data that's labeled, you'll get better results for your own models. So the good thing about weather data is you know what the precipitation was yesterday and for the last few years, for every day. And you know what the sunset. So you can actually drive pretty decent models based on that. So that is possible. So that's definitely something that's possible, provided the data is labeled. The interesting, did that answer your question? So because that is completely possible to do things on weather patterns, etc.
So the results are good.
Yeah, I mean I think we have not released one. It's actually something we're trying to do something in the open source side to see if we can build a model using NOAA data. So but the results should be possible. I would hate to create that model and do it in a live session because I'll easily find out if I'm wrong or not, especially if my model predicts it's going to be sunny and we look outside, it's raining. So, because there's always a 5% error rate. Remember that. Yeah?
You was talking about training data. What is the minimum number of data points that you need to get some decent results of deep learning?
Yeah, so this is where things like, for example, like the ImageNet model is like in the orders of, is close to, is 1 million plus images to build your ImageNet model to understand over thousands of labels, okay? Clearly, but what you can do is to figure out how can you take an existing model and then apply a smaller number of images to understand your labels. Does that make sense? So in this case, what I did was I had an ImageNet model of 1 million plus images that's already built with the weights already understood. And what I then done is I basically said, okay, can I take that model and basically extend that for two labels that I care about. In this case, the number of images I ran through it was in the order of maybe 100 for huggable and 100 for non-huggable. Make sense? So, so that's actually, but then that, I think it really depends. For example, I would not be able to use that ImageNet model and then look at medical imaging data. So for example, let's say I want to detect breast cancer in breast cancer images, right, to predict the potential character. I don't even know this, but I cannot, because the ImageNet model is run on consumer image photos, right, photos we take on a daily basis, whereas medical images is grayscale and different kind of images. You'd almost have to build like your own medical imaging model. In that case, what you want is, you can almost think of a scenario where you run through your radiology report, right? You can do its natural language processing, you understand the radiology report and figure out for that group of exams, what does the radiology report do? And that becomes your label, and then you run it across your label data set. So but I would say in general, you can almost imagine for each label, it will be in the order of thousands if you want to do a from scratch model.
When you consider a library like Keras,
Yeah.
which sits on top of TensorFlow,
Yeah.
does it indicate or does it hint some drawbacks about TensorFlow, some missing features of TensorFlow?
No, I think so. I think that's a good question. So the question was, we have higher level libraries. So I would say what it hints at is, TensorFlow is a general purpose machine learning library used both for deep learning and for structured data, wide learning, and traditional machine learning. But it's very raw, right? And I think one of the things the community is leading us is to start building higher level libraries on top of that, right? So that's where you have community generated stuff like skflow, Keras, another one. So I think what it's saying that is the community wants easier APIs. And I think that's guiding us, both Google committers and other committers, to start building those higher level libraries as part of the core TensorFlow and rather than external libraries. So I think it's just initially, I think we built it as a general purpose system, which requires a lot more boilerplate coding. And I think we want to start making all the boilerplate codes as utilities, so folks don't have to write that. Like, everybody needs a logistic regression library. Let's not write it 10 different ways. Let's just make it part of TensorFlow. And I think that will come down in the next few months. Questions?
Can you import models built by other libraries like Caffe?
It's a good question. I think in the community there's ways to convert a Caffe model and then train it into a TF. Whether you'd be able to take the weights from a Caffe model and then extend that in TensorFlow, I don't know if that's possible out of the box. Yeah?
Is there like a sweet spot for the number of labels that you should start with in your initial learning run? Or you would go in through iterations of more learning cycles as you add more labels, but is there a sweet spot that says don't?
I think it really depends on the ratio of training data you have rather than a sweet spot of the number of labels. It's like if you have enough training data for each of per label, I think the key is, so what I'm talking about is primarily supervised learning. There's also unsupervised learning scenarios, which you can just run it for doing things like clustering and scenario. But I think in general, what we've noticed and thing is people run clustering, and then when they have enough understanding of data, switch to a supervised model run in production. So in the case for your thing, I think it really depends on how much training data you have per label. So I think if you have fewer amount of training data, you're going to get wrong predictions for that label.
And you train per label?
Per label. The model, when you train a model, it's trained across multiple labels at once. Yeah. Questions? I may be getting kicked out. Guys, I still got 3 minutes, I think. Any other questions? Go ahead.
Think about the minimum size of the image resolution when it comes to training. Could it be 30 by 30?
Yeah, I think we downscale it quite a bit, but it depends again on what you're trying to do. For example, if you're trying to do something like OCR, you want really high resolution images. But if you're trying to do something like label detection or entity detection, you don't need that high resolution images. Yeah, and again, I know a lot of the examples I talked about is images, because mainly because it's always fun to do a demo with images. But you can imagine a lot of these things apply to sparse data sets too.
So, do you have a model for natural language processing?
Yeah, so actually TensorFlow we do have Word2Vec that we've open sourced. So Word2Vec is available out there. And I think we will be looking at open sourcing additional stuff on the NLP side too. I think NLP, I think you can imagine, if surprisingly, we've seen a lot of really good results of applying deep learning like recurrent models and sequence models on natural language processing. Right? I think there's a lot of really interesting scenarios there. Smart reply, which I just talked about earlier in Inbox, that's a great example of applying deep learning neural nets on LSTM-based models to drive that scenario. Basically, detecting what's the next word in that sequence. Questions? If there's no more questions, thanks again for attending. Hopefully it was useful for you guys.